Welcome to our expert training course. In this video, we will explore the core requirements that define a practical, production-ready machine learning system. We move beyond simple algorithms to understand the complexity of real-world deployment. Let's get started now by establishing the foundation for our system design. Welcome to our training on the core requirements of practical machine learning systems. When most people think about a machine learning system, they often only picture the algorithm itself, such as a type of neural network or logistic regression, perhaps focusing on theoretical accuracy alone. However, in a practical production setting, the algorithm is merely one small component of a much larger, complex system that requires extensive support infrastructure. A true ML system in production must also include crucial elements like the business goals that started the project, the entire data stack for processing information, the user interface for interaction, and the logic for continuously updating and monitoring the models throughout their lifespan. The machine learning systems we deploy are inherently complex and unique because they rely heavily on massive amounts of data, and this data changes drastically from one operational scenario to the next. For instance, two e-commerce companies might both want a recommender system, but their resulting ML systems might use entirely different features, metrics, and models because their specific datasets are unique and reflect different user behaviors. Therefore, we must adopt a holistic approach when designing these systems, looking at all components together and making sure all stakeholders, from engineers to business leaders, have their objectives considered for maximum impact. This system approach is essential to achieving successful real-world performance. Unlike focusing only on the underlying code or academic algorithmic optimization alone, we will now explore 4 specific technical requirements that define a production-ready ML system, moving beyond the simple prototype stage. Understanding this comprehensive approach is the first major step toward becoming a truly successful ML practitioner capable of deploying reliable solutions globally. The first core requirement for a practical machine learning system is reliability. This means the system must continue to operate and function correctly, maintaining its expected level of prediction performance even when faced with serious adversity, such as unexpected software malfunctions, hidden hardware failures, or simple human configuration errors. However, defining what constitutes correctness is substantially harder for machine learning systems compared to traditional software systems. Traditional software applications usually alert you immediately with an obvious error message, like a crash or a 404 not found notification, indicating clear failure boundaries. ML systems, on the other hand, frequently fail silently, hiding the degradation of quality. For instance, if you use a machine translation service and it produces a subtly inaccurate or nonsensical translation into a language you do not speak fluently, you might not even realize that the prediction system has fundamentally failed to meet its core performance expectation, even though the service appears to be running smoothly and quickly. This dangerous silent failure mode is particularly insidious, as end users might continue relying on critically faulty predictions without awareness. We must implement robust monitoring, not only for operational metrics, which track basic system health like throughput or CPU utilization, but also for ML-specific metrics, to ensure the actual predictions themselves are not garbage. A critical operational metric to track is inference latency, representing the speed at which predictions are calculated and delivered. For time-sensitive applications like predictive search or auto-completion features, if the model takes too long to suggest the next necessary character, the entire feature becomes useless, regardless of the quality of its underlying accuracy. Therefore, achieving reliability demands continuous vigilance over both system infrastructure uptime and ongoing prediction quality, ensuring trustworthiness in all deployment scenarios. This detailed monitoring must catch these subtle, hidden failures quickly before they severely impact business objectives or user satisfaction. This visualization clearly illustrates the dual nature of reliability challenges encountered when deploying machine learning systems in a live environment. The second essential requirement for any production deployment is scalability. This refers directly to the system's engineered ability to grow efficiently and handle increasing demands without sacrificing performance. Whether that involves a larger volume of end users needing simultaneous predictions, processing more input data for continuous training, or managing greater underlying computational requirements effectively. Today's most sophisticated machine learning models routinely operate at massive scales. It has become common for advanced models to contain hundreds of millions or even billions of internal parameters. Consequently, simply loading these extremely large models into the machine's memory can necessitate gigabytes of RAM, immediately posing a massive engineering challenge, especially when deploying complex models on small edge devices. When dealing with models of this expansive scale or datasets of enormous size, the training process frequently exceeds the immediate capacity of a single commodity machine. To effectively manage this level of scale, we must utilize advanced distributed training techniques, such as dividing the massive training workload into smaller, manageable tasks across multiple computing units through data parallelism, or by physically splitting the model itself across devices using model parallelism. Beyond just the model infrastructure, achieving scalability also absolutely requires stringent resource management. This crucial step involves intelligently scheduling and orchestrating computing resources, like CPU and GPU usage for repetitive workloads, ensuring all tasks run efficiently and in the most cost-effective manner possible. Furthermore, as the system exponentially grows in complexity and scope, meticulously tracking and consistently versioning all relevant artifacts, which are critical files generated during experiments, such as model weight versions, associated data splits, and precise configuration logs, becomes absolutely crucial for system consistency and reliable debugging. Scaling is fundamentally necessary to meet growing business demands and ensure that our sophisticated models can operate effectively under heavy, continuous real-world load in a cost-optimized way. Maintainability is the third critical requirement, focusing exclusively on the inherent ease with which a running machine learning system can be thoroughly debugged, systematically modified, and clearly understood by the numerous professionals involved across its complex lifecycle. ML projects mandate essential collaboration among highly diverse professionals, encompassing dedicated machine learning engineers, operational infrastructure staff known as DevOps engineers, and vital subject matter experts, SMEs, such as trained doctors or seasoned industry lawyers who provide crucial, non-technical domain knowledge. These individuals frequently use disparate programming languages, distinct tooling sets, and hold profoundly unique perspectives on the overall project goals. This intrinsic complexity makes rigorous debugging exceptionally difficult to execute quickly. For instance, if a newly deployed model begins producing subtle operational errors, the primary cause could originate from many sources: an outdated model definition file, a feature list that was inadvertently or incorrectly modified during deployment, or even a hidden issue residing deep within the complex upstream data processing pipeline. Tracing the ultimate source of these complex failures requires an extremely high degree of internal transparency within the entire system architecture. Furthermore, the ability to clearly explain how a model arrived at a specific prediction, known as interpretability, is critical, particularly in heavily regulated and sensitive industries like finance and healthcare. Highly complex, non-transparent black box neural networks are generally much harder to maintain effectively in this regard than perceptibly simpler, more transparent models like decision trees, which naturally permit clear feature importance analysis. Therefore, good maintainability demands transparent processes, comprehensive documentation, and reliable tooling to ensure that knowledge is shared, workflows are auditable, and the system can be reliably supported and quickly fixed over its entire production lifespan, enabling teams to restore correct functionality quickly and efficiently. This comprehensive mind map clearly illustrates the significant key challenges and mandatory solutions associated with maintainability in an operational machine learning environment. The central concept branches into two primary areas: complexity and debugging, recognizing that complex ML systems are large, intricate structures that are inevitably worked on by diverse stakeholders, including ML engineers, specialist DevOps experts, and crucial subject matter experts, SMEs. Debugging such an intricate system is inherently challenging because system errors can rapidly originate from multiple failure sources, such as deploying outdated code, referencing an incorrect feature list, or underlying stability issues within the upstream bad data pipeline infrastructure. Tracing these elusive issues across organizational teams and disparate tooling sets strongly emphasizes the paramount need for streamlined, transparent, and version-controlled workflows. The other major branch is transparency, where core interpretability is crucial, particularly in heavily sensitive domains like finance and medical diagnostics, where algorithmic decisions must be fully justifiable to authorities. To effectively address this transparency requirement, organizations must strategically employ solution types, like meticulous feature importance analysis, or by opting for inherently transparent models, such as simple decision trees, over complex, hard-to-explain deep learning networks. Maintainability ultimately relies heavily on clear organizational processes and reliable software tooling to manage inherent system complexity and ensure that the core prediction logic and operational decision-making processes can be completely understood and accurately verified by all relevant parties throughout the system's extended lifecycle. This critical organizational and technical alignment is absolutely necessary for successful long-term production deployment of complex ML systems. The final technical requirement for a practical system is adaptability, which is the crucial, engineered ability of a machine learning system to maintain consistent performance and safely evolve, even when the underlying data environment and incoming inputs fundamentally change. In a live production setting, real-world data is almost never stationary. It constantly shifts, evolves, and diverges significantly from the limited dataset the model was initially trained and validated on, consequently hurting the model's ability to generalize to new instances and severely degrading its accuracy. This is a major, common cause of ultimate system failure. This inevitable divergence is known broadly as a data distribution shift. There are three primary and important types of distribution shifts we must continuously monitor and address. First, concept drift, where the inherent underlying relationship between the input features and the target output label changes over time. Second, covariate shift, where the probability density or characteristics of the input features themselves change. And third, label shift, where the overall probability density of the expected output label changes. To actively combat these ongoing, unpredictable changes and maintain relevance, we rely strategically on the continual learning paradigm. Instead of relying on massive, computationally expensive periodic retraining events, continual learning actively and safely updates models in production, often utilizing extremely small microbatches of new incoming data to refine the existing model rapidly. This process mandates a rigorous evaluation step, testing a challenger model, which is an updated replica of the currently deployed champion model, against the original champion before deploying the changes live. Adaptability is absolutely essential for long-term relevance, ensuring our deployed systems remain accurate, effective, and useful in dynamic real-world environments, without requiring massive, disruptive redesigns. This proactive, controlled approach ensures maximum system stability and robustness when faced with constantly evolving variables, saving significant computational resources and engineering time over the system's lifetime. This diagram visually represents the core system challenge of adaptability and the architectural solution provided by continual learning. An ML model is initially trained and verified on a defined training data, which inevitably represents a static, fixed data distribution. However, when successfully deployed into the dynamic and live production environment, it immediately encounters real-world data, which is constantly characterized by fundamentally shifting distributions. When this divergence in data characteristics becomes statistically significant, the system experiences a measurable prediction failure, automatically triggering the need for immediate intervention and correction. This data drift is formally classified as a data distribution shift, which must be detected and analyzed via advanced monitoring systems. To resolve this continuous problem, the system strategically enters the continual learning cycle. This paradigm involves refining the existing model efficiently using extremely small data chunks, referred to as microbatches, rather than attempting to rebuild the entire complex model from scratch, which is resource-intensive and slow. This continuous feedback loop fundamentally enables the model to safely incorporate new, evolving information and data patterns it encounters in the production environment, ensuring it remains highly accurate and functionally relevant over extended periods. This process is necessarily complex because the candidate updated model, often designated as the challenger, must be rigorously tested and evaluated against the currently deployed champion model before it is permitted to fully replace it and take over prediction responsibilities. This necessity for constant, safe, and efficient updating is the key defining feature of a truly adaptable and practical machine learning system built for durable, long-term production use, minimizing performance degradation. Beyond the four essential technical requirements, a practical machine learning system must satisfy a critical contextual requirement: comprehensive alignment with definitive business objectives. If an ML system is developed specifically for a company, its primary measure of success absolutely must be tied directly to fundamental business goals, such as dramatically increasing profit margins or reliably reducing operational risk, fundamentally maximizing the return on investment, or ROI. A common and costly pitfall in many enterprise ML projects is the immediate organizational disconnect between the technical implementation team and senior management. Data scientists typically focus their intense efforts on perfecting subtle ML metrics, like laboriously pushing a model's F1 score or validation accuracy marginally higher. Conversely, business leaders are singularly focused on verifiable, tangible outcomes, such as achieved sales targets or the total successful reduction in fraud losses. Spending vast, expensive resources, including substantial compute time and skilled engineering effort, to achieve only a tiny marginal gain in a technical ML metric, such as improving accuracy from 94% to 94.2%, is generally meaningless if that marginal technical change does not demonstrably lead to a measurable positive movement in the relevant actual business metric. Before any serious modeling or algorithm deployment can even commence, the initial problem must be meticulously and accurately framed. Strategically translating a broad business ambition into a concrete, technically solvable ML task is crucial, as the operational difficulty and complexity of the job is fundamentally determined by this early framing decision. Failure to tie technical ML efforts back directly to clear, measurable business objectives often leads rapidly to project cancellation and team dissolution, even if the model performed outstandingly well in controlled academic settings. We must always ensure our deployed ML models are strategically optimized to solve the precisely correct problem for the business context, guaranteeing maximum real-world impact and maximizing the ROI of our costly deployment efforts for long-term viability. To successfully integrate and manage all the requirements we have meticulously discussed, practical ML system development must rigorously adhere to a strategic methodology, specifically the iterative process. Unlike traditional software methodologies, which might follow a waterfall or linear progression, ML development is inherently cyclical, characterized by constant and necessary feedback loops among various interdependent steps. This iterative cycle typically includes crucial stages like Step 1, project scoping, where precise objectives and technical constraints are firmly set, immediately followed by Step 2, data engineering, which involves meticulously cleaning, collecting, and labeling the indispensable training data. Then proceeds Step 3, ML model development, training the chosen algorithm using the expertly engineered features. After initial development and successful validation, the model is prepared for Step 4, deployment, where it is made operational and fully accessible to end users. Post-deployment mandates rigorous. Step 5, monitoring and continual learning, constantly checking for performance decay, data shifts, and anomalous behavior. Finally, Step 6, business analysis reassesses the project's real-world impact against its original ROI objectives. Critically, this cyclical process is explicitly nonlinear. Detailed analysis of a deployed model's mistakes might instantly force an immediate return to the data engineering stage to procure new data or refine labeling quality, entirely bypassing subsequent intermediate steps. This continuous cycling and strategic readjustment is the foundational mechanism that ensures the system remains highly robust and fully adaptable to continuously changing data and evolving business requirements, effectively integrating all previously discussed core requirements into a single, comprehensive methodology. This process provides the essential framework necessary for achieving durable, long-term production success and continuous value delivery. The final concept we meticulously cover is the essential supporting pillar of infrastructure and tooling. ML systems are complex, and robust infrastructure is absolutely necessary to automate complex processes, drastically reduce the occurrence of human-introduced bugs, and actively enable ML practitioners to efficiently meet all the core requirements we discussed: reliability, scalability, maintainability, and adaptability. Infrastructure can be strategically conceptualized in distinct layers. At the foundational level is storage, utilizing highly commoditized services like Amazon S3, and compute, intelligently allocating critical resources such as CPUs and GPUs. Above this essential layer resides the development environment, standardized throughout the organization, often using container technology like Docker. Docker provides reproducible, step-by-step instructions to flawlessly recreate a system's required software environment on any hardware, which is crucial for maximizing maintainability and scalability across the organization. Many cutting-edge companies centralize capabilities by utilizing an internal ML platform, which offers standardized, generalized infrastructure across numerous different ML applications. These platforms typically incorporate specialized tools for managing model artifacts, storing features consistently, and monitoring system health, which collectively help centralize maintenance efforts and significantly reduce inconsistencies. Furthermore, workflow management tools, such as schedulers and orchestrators like Apache Airflow, are utilized extensively to define and automate the inherently repetitive nature of ML tasks, like daily model retraining or generating large batch predictions, essential for efficiently maximizing adaptability and consistent performance at planetary scale. In summary, infrastructure takes the technical complexities of machine learning like distributed training and continuous updates, and effectively transforms them into manageable, automated, and repeatable organizational processes, fundamentally making it the indispensable bedrock of modern practical ML system design and continuous operations.